Define these wave characteristics with a couple of standard symbols and then tie in some basic equations. So, like we talked about before, wavelength, we use the Greek letter lambda. The metric unit will be in meters when we want to measure the size of a wave. So one thing that's interesting as a little bonus project would be check out the size of the radio antenna on top of the school for our radio station. I think we're 88.5 WHSD, which is 88.5 megahertz. And I bet the wavelength of the broadcast frequency, 88.5 megahertz on the FM dial, is pretty close to the size of our antenna on top of the school there. The period is the time for one cycle of the wave to generate itself. So the inverse of the period is what we call the frequency, the letter F, and it's the cycles per second, and we just call that the hertz. Not to be confused with the rental car company, but in honor of a German scientist who did a lot of studies with waves, in honor of Hertz. So HZ is the abbreviation. So maybe one example is if you have a cordless phone. In the old days, we had 900 megahertz cordless phones, and we have 2.4 gigahertz, and now there's 5.8 gigahertz. And all that means is, in your cordless phone at home, the electrons inside that antenna will jiggle 5.8. Giga means billion times per second. And so basically the higher the frequency usually means higher energy, so usually it's a clearer phone call. That's the way to think of it. You might have seen those terms too if you're shopping for computer stuff, like the speed of a processor, like an Intel Quad 4 2.8 gigahertz processor. And all that means is the computer's clock jiggles back and forth the electrons 2.8 billion times per second. Finally, we can come up with what we call the wave velocity equation, which is the speed of how fast the wave is going. Now speed is just distance over time. In fancy physics words, speed we want to call, instead of just speed, we use velocity, because velocity is a better definition. It's speed with direction. So if you recall, velocity is your change in displacement over time, your distance over time. But another way to look at that is it's your wavelength times frequency. Instead of distance, we're going to use wavelength. And instead of time, time is 1 over the frequency, or frequency is 1 over the time. So in other words, if you look at the units here, we have meters, and then frequencies in hertz are 1 over seconds. We get meters per second. So maybe another way to look at that is if you think of a runner like a sprinter, like Usain Bolt, we could figure out how fast Usain Bolt is running to set another 100-meter world record by just taking distance over time. But another way to look at it is to think of Usain Bolt as a wave, which is kind of weird. And the way you can think of that is he's such a fast sprinter because he has a long stride length. That's like his wavelength. And then the frequency is how often he can repeat the cycles of running, how quickly he can move his legs. So he can move his legs 5 times a second. That would be a frequency of 5 hertz. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The period would then just be 1/5 of a second if we wanted to solve for that. So in other words, it takes 1/5 of a second, 0.2 seconds, for him to have one stride, would be the way to look at it there.